In this section, we're going to talk about something called a basis. So it turns out that if we have a set of vectors that are both linearly independent and spans a certain vector space, then we have created what's called a basis for the vector space. And what that means is that any vector in that vector space can be written as a linear combination of those basis vectors. So let's look at some examples. We're going to start with one that's really simple that we have been using since you started talking about vectors, probably in a pre-cal class somewhere. And that's your vectors I, j, and k. So example 1 is giving you the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So those are called your standard basis vectors. And we're usually used to referring to those as I, j, and k. Now what's nice about those is that those are unit vectors, which means they have a length of 1, and that any vector can easily be written as a linear combination of those vectors. Now, what I'm going to show you is that these three vectors match that criteria. It's going to span all of that vector space, and it's going to be linearly independent. So let's start with spanning all of R3. So to show spanning, we want to show that any vector can be written as a linear combination of those vectors. So I'm going to call my generic vector ABC. So we have C1 plus 0, C2 plus 0, C3 is equal to 0, C1 plus C2 plus 0, C3 is equal to B. And then 0, C1 plus 0, C2 plus C3 is equal to C. So there's only one solution to this system, and that's if C1's A, C2's B, and C3's C. So this guy definitely spans R3. That means any vector in R3 can be written as a linear combination of those three vectors from R3. Now let's show independence. That means that C1 times vector 1 plus C2 times vector 2 plus C3 times vector 3 is equal to the 0 vector if and only if C1, C2, C3 is equal to 0. So if we were to distribute, we would have, and set up our system, C1 plus 0, C2 plus 0, C3 is equal to 0. 0, C1 plus C2 plus 0, C3 is equal to 0. And then 0, C1 plus 0, C2 plus C3 is equal to 0. So our solution is the trivial solution, which means that these vectors are also linearly independent. So since they're independent, since they span, then therefore we have a basis. So therefore, S forms a basis. And this is for R3. Now let's look at that next example. In example 2, we have two vectors. We want to show this forms a basis for R2. So this is not the standard basis for R2. The standard basis for R2 is I and J. So we have to show both of those again. We have to show spans and then independence. So let's look at spanning. If we take C1 times V1 plus C2 times V2, can we form any vector in R2 by taking that linear combination? That's what we want to answer. So there's our system. Now, to have a unique solution to the system, we have to have a matrix that's invertible here. We're thinking about this as AX equals B now. So A must be invertible. And one way to check that is to check the determinant. So we get -2, which is not 0. That means that A is invertible, which guarantees a unique solution. And since there is a unique solution, then that means this must span all of R2. So what that means is that any vector in R2 can be written as a linear combination of those two vectors. Now we need to show independence. So we're setting up our system again. Only now we're looking at a homogeneous system to solve. So C1 plus C2 is equal to 0. C1 minus C2 is equal to 0. Let's do REF. And this tells us the only solution to this is if both C1 and C2 are 0. So since the only solution is a trivial solution, then that means this must be a linearly independent set. So what that means is neither vector is a scalar multiple of the other vector. So because we span and are independent, then therefore S forms a basis for R2. So a basis is your smallest set of vectors you would need to be able to span that entire vector space. So for R2, you have to have 2 vectors. Now notice these vectors are not the standard IJ vectors. You don't have to have IJ to span all of R2. You can have different vectors that span all of R2, which means you can write any vector in R2 as a linear combination of these 2 vectors, just like you can with a linear combination of your IJ vectors from R2. So it's pretty neat to start thinking about things in terms of non-standard bases. Let's look at another one. Let's look at 3. We're using this set, and we're going to show this is going to form a basis also. And so we're going to go through that same process. We need to show spanning and we need to show independence. You do have to show both. This is where you may want to pause the video and try it on your own. And then come back and check your solutions. So example 3, we need C1. I'm going to show spanning first. C1 V1 plus C2 V2 plus C3 V3 is equal to ABC. You want to show any vector. So here's any vector in R3. Can be written as a linear combination of these. So there's our system. C1 minus 2C3 is equal to A. 2C1 plus C2 is equal to B. 3C1 plus 2C2 plus C3 is equal to C. Now we want to know, is there a unique solution? So we're going to check that determinant. And I got the determinant to be -1, which is not 0. So since we have a non-zero determinant, then that means that there exists, I'm using the backwards E for there exists, a unique solution to this. And since there's a unique solution, then this set does span. So now we have to check independence. So we've got C1 minus 2C3 is equal to 0. 2C1 plus C2 plus 0C3 is equal to B. 3C1 plus 2C2 plus C3 is equal to 0. Sorry, this B should be a 0. Typo. RREF. So if they are independent, then that means we should only get the trivial solution here. And we're going to get the identity here with zeros. So that tells us C1 has to be 0, C2 has to be 0, and C3 has to be 0. So since we only get the trivial solution for that particular system, then that tells us that these vectors are independent. So since they span, since they're independent, then that means they form a basis. So that's really all there are to finding a basis is, does it span? Is it independent? It has to meet both criteria. So let's look at one that's a little different. Let's look at a vector space P3. So P3 is a set of polynomials degree 3 or less. So we've got vector 1, vector 2, vector 3, and vector 4 here. So you have to show both items. So let's start with spanning. C1V1 plus C2V2 plus C3V3 plus C4V4 has to be equal to the a generic polynomial. So A plus BX plus CX squared plus DX cubed. We're looking at P3. So if we compare coefficients on both sides, we have x cubes, x squareds, x's, and constants. This is just to help us organize. On the left, we have a C4 x cubed that has to be equal to D. We have a C3x squared, which has to be equal to C. We have a C2x, which has to be equal to B. And then we have a C1 as our constant, and that has to be equal to A. So there's a unique solution for each one of these. If we had a specific polynomial, we know what A, B, C, and D would have to be, which means this spans. Now let's check for independence. Pretty much the same setup. The only difference is what's on the right-hand side. So we're comparing coefficients again for x cubed, x squared, x, and then the constant. So we have C4 has to be equal to 0. C3 has to be equal to 0. C2 has to be equal to 0. And then C1 has to be equal to 0. So the only solution is the trivial solution, which means that we are independent. So since we span, since we're linearly independent, therefore we have a basis. Now, this set of vectors in example 4 is actually considered your standard basis for P3. It would be really easy to write any third degree or less polynomial in terms of those 4 vectors in that space. So we could go through example 5 the same way. This is actually considered the standard basis for M22. Notice we've got a 1 in the top left here, top right, bottom left, bottom right, and everything else is zeros. So this would be really easy to write any 2x2 matrix in terms of these 4 vectors in this space. But let's go through and we'll go through and prove this one too. You have to show both things, spanning and independence. So we want to be able to write any 2x2 in terms of those 4 matrices. So if we compare top lefts, we have C1 plus 0 plus 0 plus 0 has to be equal to A. So C1 has to be equal to A. We have C2 is equal to B. C3 is equal to C. And then C4 is equal to D. So unique solution, it would be unique depending on what A, B, C, D are, which means it spans. So if we check for independence, there's our setup. So C1 is going to have to be equal to 0. C2 is going to have to be equal to 0. C3 coming from here has to be equal to 0. And then C4 has to be equal to 0. So the only solution is the trivial solution, which means that these vectors are linearly independent. Since it spans, since it's independent, then it forms a basis. So therefore, it forms a basis for M22.